Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Hi students. So today we're going to continue with our electrostatics, study of electrostatics. Last class I spent a little time going over the portions breakup, and this portions breakup is almost true for all the any engineering college, etc. So I thought I will, before I quickly jump into jump into the details, I will briefly reiterate that portions. Okay, so I hope you can see my screen. Yes. So again, for various students, our two leading platforms for students who are interested in NEET, we have Sushruta for NEET, which is available from the Google Play Store. Download the app, go about registering, and then you are underway. Okay. Now, if you're a JEE student, you should go to com.JnanaMarga.Ramanujan. Okay, and go to Play Store, and download the Ramanujan app. Install. It has to be a Android phone. Remember, we don't work on iPhone. It has to be an Android phone or Android tablet. If you want to use our tablet platform, we also have a slightly higher entire tablet phone, but that comes with books as well. We give you both the tablet and the books, and then you can study for 2 years with it. Okay, so now this is the formula sheet. It is there in your NCERT textbook. Okay, now I want you to understand this formula sheet and understand the things that we started. We started with electrostatic force, then we went to electric field, right? Field is newtons per coulomb. It is the force per unit charge. If you kept a unit charge in one spot, what is the corresponding force it will experience? That is called the electric field, and it is a vector. It's like, because force is also a vector, right? Now, then we introduce this idea of electrostatic potential. Okay, that today we are going to be discussing Gauss's theorem, which deals with this related idea, which idea is slightly related to electric fields, called flux. Okay, now flux, I will come to flux later, but we also discussed dipole moment, we discussed potential and work, right? And then we discussed a few other related topics. But before I go any further, I want to re-emphasize what I emphasized the last class, which is the weightage. Okay, see, today we are in our previous lecture, that is in the Saturday morning lecture, we cover the red part, this part, right? Mechanics. So we went kinematics, Newton's laws, right? And then then the third part, which is work, power, energy. Then we go rotation. Then we will close it out, right? With more electrical mechanical properties of matter, etc. Right? So that is roughly, if you see, about a little more than a third, almost a third, or maybe even just slightly more. Okay, so now on this side we are now in this yellow section, as you know, right? And here we will cover the yellow section, then we'll go to the purple section, right? Electrostatics, then we will go to current electricity, then we will come back and complete the magnetism part. Okay, now these two parts are roughly one third. The other one third is three different topics: modern physics, optics, and heat and thermodynamics. Okay, now of these three, heat and thermodynamics, You should learn all the parts dealing with Carnot engine, etc. We just completed that. If you want to see the old lectures, you can go and see it in our YouTube channel. They are all listed in the YouTube channel. Then see, everything we have done once before, and you can get all that in the YouTube channel. Now, but I'm giving you this weightage so you know this number. So you should focus now electrostatics and then current electricity and electromagnetic induction, right? Now, JE has a very similar weightage as I explained last time. You have about one third going. If you see here, actually JE little bit less, surprisingly enough, right? Kinematics, rotational motion, work power energy, physics and measurement, right? Laws of motion, gravitation, they all have little bits. Okay. If you see, in fact, electronic devices, right? If you see these sections, right? 1, 2, 3, 4, 5, right? These 5 sections, in fact, have almost 24 plus 9, 33 plus 5, 38%. Okay. Optics, modern physics, communication systems has more weightage in JEE. Okay. So students who study JEE, you should spend more time there. Electrostatics and current electricity also have 20%, significant amount of marks there, right? So you should build that 23, 24% go to, or 20, 25, 26% go to electrostatics, another 30% goes to, so it's 40, 30, 30. A little bit less for, what is that, mechanics, okay? And JEE physics is very important, okay? Um, so now I'm not going to go over all this because if you have missed all this, you should go and see the old lectures, okay? But after we did dipole, I explained dipole, I, I thought I should re-emphasize one or two ideas in electrostatic potential. Okay? See, electrostatic potential is related to the idea of work in a conservative field. Okay. Now, what are conservative fields? Conservative fields are fields where the force is a function of purely the position, or more specifically, it is if you keep two fixed charges, two fixed bodies, right? It is the distance that separates them it is essentially a function of that. Okay, so it can, but the thing with electrostatic potential is, that in an electric field, we say that electric fields are also conservative fields. It is a concept. Electrostatic potential is a concept similar to potential energy. Okay, electrostatic potential is the work is linked to the idea of work being done. Okay, and that work is very specifically related to the position of the charged particle or body in an electrostatic field or electric field. In an electric field, it is the work done to bring a body from infinity to that point. Okay, that is electrostatic potential, right? So now, if the charge is, let's say the electrostatic potential, the electric field is created by a positive charge, right? And you have a positive charge in your hand, right? Remember, like charges repel, so it takes a lot of work to bring it to that point, right? If on the other hand you have a negative charge, it will automatically come by itself. In fact, it takes effort to pull it away, right? So like poles, like charges repel. Okay. Now, electrostatic potential is the work done by bringing an external force, the work done by an external force in bringing a unit a positive charge from infinity to the point in the electrostatic potential. So take unit charge from infinity, you bring it here, right? So now, if you had to move it from one point here to another point, So what is that work? Q by 4 pi epsilon naught r. So what is the electrostatic potential? If you want me to define it, I have a formula for it. You have point charge and you are at distance r from the point charge. It is Q by 4 pi epsilon naught r. Right? Now, what do we say if you have a line charge, a sphere of charge? They're all, you do integration from the point charge. Okay? You just use the superposition principle. Okay. So now, in the case of and so what does it take to bring the unit charge from infinity, unit positive from infinity to a particular point, right? Now we also introduce this idea of a potential difference. The potential difference between 2 points in a particular electrostatic field, right, is Q by 4 pi epsilon naught r by r1 minus Q by 4 pi epsilon naught r2, right? Now, if you wanted to find the energy, you just multiply it by the particular charge, because we discussed unit charge. If you had a charge of say 5 coulombs, just multiply it by 5 to give you the energy, right? The potential times Q will give you the energy. Okay, so what the electric field is to force, the electrostatic potential is to energy. Okay, and therefore the electrostatic potential is a scalar, electric field is a vector, force is a vector, similarly work is a scalar, right? So these are the equivalents. Okay, so and again you can apply superposition, can be applied to potential energy and work, right? You do work and it becomes potential energy, right? Like when you have a book, I lift it up, I do mgh work, its potential energy increases, I let it go, it will become kinetic energy. Like that, if you you move the particle, right, and then you let it go, it will start moving and it will develop kinetic energy, right? Energy can neither be created nor destroyed, only it gets transformed from one form to another. So potential energy in the form of electrostatic potential can be converted to other forms of energy. And one of them is, of course, kinetic energy. Okay, so much for that. Okay, so we will be discussing many different related laws associated with this, but right now we are starting just with electrostatic potential. Okay, we'll be discussing the interaction between electrostatics and magnetism, which is a very big part of everyday life. Okay, now we have motors and then we have generators. So now electrostatic potential is 1 minute. Hi, welcome. Were you able to join? Okay, perfect. So I'm going to continue. I've just started, and I will continue. So we're still discussing what we were doing last class. Little bit I'm discussing electrostatic potential. Okay, one related idea to electrostatic potential is this idea of electro, surfaces and lines which have a common electrostatic potential. Okay, so if you have a point charge and you put a circle around it, right, all the points in that circle will form what is called, and let's say we deal with it in 3 dimensions. Okay, so I have a point charge, so very small point, it offers very small point, right, point charge. Now I have a sphere around it. Okay, and that sphere is a hollow surface. Okay, a circular thin sphere. Okay, now this thin sphere, every point on the sphere has the same electrostatic potential. Okay, now because if you want to bring a unit charge from infinity to a point on that electrostatic potential, right, you will then end up with you will do a certain amount of work, right? And the same applies to every point um, 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 on that surface. Okay, so every point on that surface, you do the same amount of work to bring a unit charge from infinity to that particular point. Okay, now what is important is that that surface is said to be a surface of equipotential surface. Okay, all the points have the same potential. Okay, now because electrostatic potential is a scalar, so the value on all those points is the same. Okay, now we are going to introduce a related set of ideas, and so we introduced also this idea of work in the context of in an electrostatic field, right? We said that if that work done in an electric field is path independent. That is, the amount of work it takes to go from A to D by going from A to B to D, A to C to B to D, etc., you end up with exactly the same amount of work. Okay, the regardless of the path you take, you will end up with the same amount of work, right? To go from A to D. Now, in addition, to go from what is that? To go from A one full circle and come back to A, the amount of work you will do is zero. You go one full circle, sometimes you are doing the work, sometimes work is being done for you, on you. So if you are at the same point, the electros the work done in an electrostatic field is zero if you come back to the same point. Okay, so that is how it works. All right. So like let me explain it with an equivalent in terms of energy, right? See, the Earth's gravitation field also is a conservative force. So now let us say I throw this up, right? I throw this up, I impart it a particular force, I increase its potential energy, right? Now, when it goes up, it is, I impart it certain kinetic energy, right? When I push it, I push it with certain kinetic energy. As it goes up, the total energy is conserved. That is, the potential energy plus the kinetic energy is conserved, right? At the highest point, it has the most potential energy and zero kinetic energy because it has slowed and stopped. At the topmost point, for a very brief time, it is going to stop. Then it's going to reverse and start coming down, right? As it reverses and starts coming down, the highest potential energy, slowly it will lose potential energy as it is coming down. It's moving faster and faster, so its kinetic energy will increase, right? Up until the point that it reaches here, right? Similarly, also with electrostatic potential, right? It is also an inverse square law. It also follows this rule that that there is it is a conservative field, which means that total energy will be conserved. Okay, so that remember that. Okay, so the total work done by the external force in moving from A to B to B via D is also the same. So that's the whole idea in this figure. Okay, so multiple paths you take to go to C to B, work done is EQ times X minus XF minus XI. Here also EQ times XF minus XI. Regardless of the path you take, it's only the end states that matter. That's why we say it is independent of the path followed. Work done is independent of the path followed. Therefore, we say it is a conservative field. That's the nature of behavior in a conservative field. Okay. So having said that, I'm not going to go through these examples. You should see the videos in IIT PATH. Okay, these are all the slides here are taken from IIT PATH. So if you go a full circle, path independence tells you that if you go a full circle, you will come back to the same point. So I am now going to briefly tell you something. Okay, so this F dot dl, right? That is the work done, right? So the net work done will be zero, right? Now, electrostatic potential, on the other hand, is E dot dl, right? So you do remove the charge out. Okay. So one thing I'm going to tell you is that when they put that integral, they put that circle, right? It can mean more than one thing. Okay. When they discuss this, right, what they are saying is when they put that circle, here they are talking of what is called a line integral. They are doing f dot dl over a line. Okay, it is doing, because dl, the object itself is tracing a line, right? It goes like this, it goes some particular direction, right? So they are doing what is called a line integral. So when you do work, right, you follow a line integral because you're doing work, and as you navigate, you're calculating the force. The force keeps changing at every point in the field, right? So you do f dot dl, 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 right? So that kind of an integral is called a line integral. Okay. Now, why I'm telling you is because today I am going to introduce to you this idea of Gauss's law. Okay. Gauss's law introduces, in addition to all the terms that you have learned so far, charge, electrostatic force, Coulomb's law, electric field, which is a vector, charge, force per unit charge, electrostatic potential, work per unit charge, right? Now we are going to introduce this new term called flux. Okay, flux, roughly speaking, equals E dot ds. Okay, now what is E? You know, electric field. ds, on the other hand, is a vector which represents an area. Okay, dl you saw in just now, right? Dl, right? F dot dl, right? Dl is a vector. This is a displacement vector, right? Now ds, on the other hand, is an area. Okay, so E dot ds, right? And how do you represent an area, right? Now the vector associated with an area is the vector associated with an area is represented as follows. Let's say you take a very minuscule area, right? Because always you deal with dx. In calculus, you always deal with minuscule things. So it's a very small area. Like let's say, I talk of my palm of my hand is an area, right? So I take a very small piece of that area. Okay, then, and what I do is I I take the area in my hand, and I create a vector for it, and that vector is, the direction of that vector is normal to the area. Okay, so now if I hold my hand together like this, I make a what is called a closed surface. Okay, and Gauss's law deals with these closed surfaces. Okay, so you can create any kind of surface. In Gauss's law, it deals with imaginary surfaces that you create. And what Gauss's law states is that if you do this E dot ds over the full surface, E dot ds, 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 over any closed surface, if you do E dot ds, the net result of all that E dot ds over the whole closed surface will nearly equal the enclosed charge divided by the constant epsilon naught, right? If you remember epsilon naught, 1 by 4 pi epsilon naught q1 q2 by r square, Coulomb's law, right? So that epsilon naught, okay? So closed integral of E dot dA equals q enclosed by epsilon naught. Okay, and closed integral of E dot dA is called flux, is the total flux. E is a vector, ds is another vector, the dot product of two vectors is a scalar, so flux is a scalar. Okay, think of it like there were rays or water or some kind of flow. Okay, flux is a kind of flow. Okay, so if you think of flux as a kind of flow, right? The flow of this flux, okay, around a closed surface, okay. So E dot dA around that closed surface will equal the enclosed charge divided by epsilon naught. That is Gauss's law. When it is stated differently, Gauss's law is also called Maxwell's first equation. Okay, so Maxwell's first equation is also Gauss's law. Okay, so and what it states is, so now let me give you an example. Look at this surface. This is assume that this is a closed surface. So now I have a closed surface. Inside the closed surface, there are two charges, Q1 and Q2. Okay. Now, what is the total flux emanating out of this closed surface? The total flux is, how do you evaluate it? It is E dot dA, right? Now, what Gauss says is that the total flux emanating out of this from this closed surface, that if you do E dot dA, E dot dA, E dot dA, and you integrate it all over that surface or any closed surface, that will equal the enclosed charge divided by epsilon naught. It is a law that it will equal the enclosed charge divided by epsilon naught. Now let me ask you the counter question. Let us say Q1 is a positive charge, Q2 is a negative charge, and Q1 equals Q2 in magnitude. So it is let's say it is a dipole, right? You put a closed surface around it, any closed surface around it, okay? What will be the flux? It will be zero, because the enclosed charge is, net enclosed charge is zero. Let us say I make a closed surface and there are no charges here, but all around there are charges. What will be the total flux in that enclosed surface, around that enclosed surface? It will be zero, because it does not enclose any charge. There is only charges everywhere around it, right? It is like saying water everywhere, but not a drop to drink, right? When you are in the ocean, it is like that, right? So it is like this. So if the surface does not have a charge inside, then there is no flux. E dot dA is over the closed surface will be zero. There will be E somewhere, there will be E here, there will be E there, there will be E there, there will be there, there will be E all over the surface. But E dot dA will cancel, when added, when it is all summed up, it will cancel each other out. Okay, so that is it's a very counterintuitive law, but you must learn it, because they will ask questions about it. Otherwise, you will say, no, I have so many other things to learn, right? Okay, so it is typically taught in two forms. I don't know if you want to learn all this, but I will tell you briefly. So flux is Q by epsilon naught, where phi epsilon is called the electric flux to a closed surface S enclosing any volume. Okay, now Q is the total charge enclosed within the volume, and epsilon naught is the electric constant, right? Now, so phi E equals the closed integral E dot dA. So E dot dA equals closed over a closed surface equals Q by epsilon naught. So last time here we discussed a path integral. We drew the same thing, put one circle and said it's a path integral. Here we are not discussing a path integral. Here we also drew the integral and put one circle. This is a surface integral. Okay, so whether it's a surface integral or a path integral is determined by whether you have a dA or whether you have a dl. Okay, so now here what you are doing is you are evaluating the flux. Flux equals Q by epsilon. Flux is closed integral of E dot dA. Okay, now there is this theorem called the divergence theorem, which says that del dot F dV equals E dot dA. Okay, now if you apply the divergence theorem, then you will end up with del dot E equals rho by epsilon, which is the differential form of stating Gauss's law. Okay, that comes from if you take this Del dot V dV equals E dot dA. If you take this, right? If you take this, then you will end up with that. Okay. So, but this is not very important. Just remember this. This is Maxwell's first equation. Del dot E equals rho by epsilon, where rho is the charge per unit volume. Okay, charge density. It's called the charge density. Charge per unit volume is called charge density. It's called rho. Okay, so this is as a result of divergence theorem. You don't need to know. When you have to know, you know, if you become engineer and and you work in electricity magnetism, they will teach you this in great detail. So then you learn it. Okay, so now Gauss's law deals with electrostatic static flux. Flux is like a fluid. Think of it like fluid or volume flowing. Okay, flux, fluid, right? Think of it like that. It's like a fluid flow. It is like, see, if E is, if the electric field is intense, then you have more flux. E dot over a unit area, you have more flux. So it is electric field flowing from a charge out into the surroundings. Okay, so it is a, how can I put it? You know, it is like fluid flow. Okay, fluid flowing with a uniform velocity. It's flowing faster. You say there is more flux, right? There is influx, outflux, right? Inflow, outflow, like that. Influx, outflux. So flux can be thought of as fluid flowing faster. Okay. Now, but here we are not talking about fluids. We're talking about charge. We're talking about field. Okay. So field is thought of as, you know, flowing. Okay. So it's a little bit tricky business, but what you need to remember is that we deal with this law. Okay. Closed integral of E dot dA equals Q enclosed by epsilon naught. Remember this law because we will be applying it in many places. I already defined the vector area, right? You have the surface. You take a small box ds, right? The vector area, the vector for ds is normal to the surface. Okay, so E dot dA, if I have A like this, at every point I draw a normal vector. That is the direction of the vector. So if I have a vector like this, I put one a j like that. So you can see, right? X, if it is in the xz plane, if the area is in the xz plane, the vector is j along the y direction, which is normal to the xz plane, right? So if it was in the xy plane, it will be k. Okay, so if it was in the yz plane, it will be I. Okay, so I hope you understood that. So that is how this electrostatic flux works. You have a closed surface. Let's say you make a cubic surface. That's when you will have I, j, k, etc. Okay, so now let us say there is a point charge somewhere inside this cubic surface. On this side, what will be the flux? It will be like this. On this side, on this side of the cube, what will be the flux? It will be like this, or not flux, E. What will be the E, right? E will be outward. What will be the E on, you know, if you had a unit charge, right? It will be like that and like that, right? And so if you did E dot dA, right, the flux will be only in one way, right? So if you had a uniform field, E dot dA will be like that. Okay, so please understand what is the net flux that flows through a closed cube in a uniform in a uniform field, right? What will be the net flux? It will be zero. But why? Because the E dot dAs will all cancel out, right? See, the E dot dA on this surface is this way. The E dot dA on this surface is that way. So this E dot dA, that E dot dA will cancel out. But why is it all going to be cancelling out and being zero? Why is it all finally going to be zero? That is because of Gauss law, because there is no enclosed charge. There is no charge inside that cube. The net flux is only determined by the charge inside the cube. Okay, so you remember that, then you will be able to answer a lot of the Gauss law questions. Gauss law is not easy, but it's not difficult either. If you understand it well, it's not difficult either. Okay, so see, he is showing you a cube and he is showing you the various surfaces and the corresponding S vector. Okay, on this, for this surface, the top surface, the S vector is, see, this is I, this is J, right? So this surface is parallel to the IJ plane, right? So the normal will be K. So if you see, this is X, this is Y. So the normal to this surface is along Z, and along Z is K. Okay. So now this surface, right? That surface is facing the other way, right? Now, if this is I, and this is K, it is in the minus J direction. So it is along the Y, right? It is parallel to the Y axis, right? So because if it is, if it is on the XZ plane, the perpendicular will be negative Y, along the negative Y. Okay, and similarly for this one, right, the perpendicular is positive J. This is along the positive Y axis, therefore it is positive J. Okay, so the other one is minus SI, this one is plus SI. Okay, so what is the magnitude? The magnitude is just the area. Okay, if you define the area, the magnitude will be the area. The direction is only normal. Okay, so now if you know the E, his E, you look at his E. His E is like this. Okay, he is defining an E which is parallel to the Y axis. Okay, now what is E dot ds for negative SJ surface, this surface, right? E is like this, S is like this. Okay, so E dot S will become just minus ES. The dot product of two parallel vectors is just the product of the two vectors. Cos 0 is A dot B is AB cos theta, because theta is 0, cos 0 is 1, right? So E dot S is just E dot S, right? But they are in opposite direction, therefore it will be negative ES. Okay, so that is, if you see, he is talking about this phi 2 in this phi 2. Okay, now for HCDI, right? For HCDI, E is positive, S is positive, it will be positive E times S, right? And the angle is 0, right? Now, for the other four surfaces, E is like this, S is like this, or like this, or like this, right? Or like this. So, when E is like this, S is like this, or like this, or like this, or like this, right? If that is the case, E dot S in each of these cases will be dictated by not E or S, but by the angle between E and S. If E and S are perpendicular to each other, what is the angle between them? 90 degrees. What is cos 90? So it is ES cos 90. Cos 90 is 0. So if they are perpendicular, the value is 0. Okay. So the net flux is the flux on phi 1 minus the flux on plus the flux on phi 2. The flux on phi 1 is ES, the flux on phi 2 is negative ES. So the net flux on that cube is 0, because it will cancel out. Okay, the other four surfaces, right? FIHG, right? ABCD, right? then GHCB, FIDA, right? All those four surfaces will have E dot dA being 0 because E and S are perpendicular to each other. All right. So, and these two, they cancel out. So, Gauss's law states that because there is no charge inside the cube, there will be the net flux on that closed surface will be 0 because it contains no enclosed charge. Okay. So now let's say he rotates the cube. You rotate the cube, it will still be 0. Why? Because there is no enclosed charge. There is still no enclosed charge. Okay. So regardless of how you rotate and all that, Gauss's law tells you there is still no charge. So the point with Gauss's law is that it is very counterintuitive, okay, but it is very simple if you understand it. Okay, so that's the important thing. You try to fully understand this. If needed, you see the video, see the IIT PAL video, then you will understand it even more. So now here he has a point charge in a sphere. Okay. Now the E on at every point in the sphere is 1 by 4 pi epsilon naught q by r square, and the r vector is always outside, right? The s vector is also normal. The E vector is always normal. The s vector is also normal, right? So ds will also be normal. So you will find that it is just q by 4 pi epsilon naught, and therefore E will always be q by 4 pi epsilon naught r square. The ds and E will always be parallel to each other, right? And ds will always be unit vector, and therefore when you do all the ds's, right, it will be the surface area of the sphere. Okay, so because it is symmetric, all the ds's will just become the surface area of the sphere. Okay, surface area of a sphere is 4 pi r square. Okay, so the net flux will be E times 4 pi r square. So E times 4 pi r square is the net flux. That will equal the enclosed charge, which is just q. It's a point charge of q by epsilon. E by 4 pi epsilon r square will equal q by epsilon. So E is q by 4 pi epsilon naught r square, like you expect. Okay, so this is one way to also calculate the electric field. Okay, you of course know that at every point it is going to be the same thing, right? E by 4 you just know from without using Gauss's law also, right? But remember, understand Gauss's law in the context of a sphere. Very, very important to know if you want to solve all problems with this. Electric flux to an arbitrary surface, basically arbitrary closed surface. Also Gauss law works, and the basic point here is if you look at the enclosed charge by that closed surface, q by epsilon naught will give you the flux to the surface. Okay, so here he has many examples, all of which where he is telling you the same thing. Flux equals, if he has three charges here, he has a closed surface around these three charges, q1, q2, q3, q1 plus q2 plus q3 by epsilon naught will equal the total flux. Okay, so the definition of flux and the understanding of Gauss's law. So they use Gauss's law to calculate many different the electric field in many different kinds of bodies. Okay, so now let us consider the conductor. Okay, a conductor is typically a metal, right? If you look at this wire, right, this is I use this wire to charge my cell phone, okay, or to charge this my earphone. Okay, now inside this wire they have this, they will have copper. Most common element used inside a wire will be copper. Sometimes they use aluminum, but it will be a metal. Mostly it will be a metal. Okay, mostly. Now metals are the most common conductors, okay, used in electricity and magnetism. Okay, so inside there will be copper. Don't cut any wires in your house, and get into trouble. But take it from me. Okay. Outside they will put something like they will put an insulator. Why? You don't want to get a shock, right? Uh, so inside they will put a conductor which is metal. Okay. So now what happens inside a conductor is like all the charges. So, and then what do? You connect it to the power source, right? Now, the power source was driving electrons through the wire. Okay. Now, if you connect it to a battery, the battery will push electrons from the negative from the cathode to the anode, right? And we say that current flows the other way around from the anode to the cathode. Current flows in the opposite direction of the electrons, right? So now you connect this between this and my earphone. It will charge my earphone, right? And so when I charge my earphone, then electrons flow, right? When electrons flow in a conductor, they will go to the surface of the conductor. Okay, inside a conductor, there is no electric field because of Gauss law. Because all the electrons will flow only on the surface of the conductor. So if this is a conductor, right? Let's say this is a conductor, all the electrons will only be on the surface side, and it will flow like that on the surface side. Okay, inside let's say you have the conductor, right? Inside the conductor, no electrons will flow. Okay, and therefore, if you draw a Gaussian surface inside a conductor, the net flux will be zero because there is no charge inside the conductor. Okay, so remember that. That's a very always tested item. So so the enclosed charge Q, right? So simple application of Gauss law. First is the conductor. Inside the conductor there is no charge, therefore there is no electric field, right? Now simple application of Gauss law, enclosed charge and the dipole. I already told you, if you have a dipole, the total, you cover the dipole which has a positive and a negative charge, right? So the net flux will be zero around the hole if you cover both of them together, right? If you cover only one, each of them will have a q by epsilon, the other will have a negative q by epsilon, because one is the positive charge, the other is a negative charge. Okay. Now, if you had a conductor and you covered the whole conductor, right? So if you had a conducting sphere, right, all the charge will uniformly spread to the surface of the sphere, right? And then you drew a Gaussian surface around it. Therefore, then you will get Q by the surface charge density will be Q by 4 pi epsilon naught, Q by 4 pi r square, right? So it is uniformly spread, means you have Q by 4 pi r square. Okay. So enclosed charge Q at distance K from the center, which is E. Okay. So using symmetry, the electric field will be Q by 4 pi at a distance K from the center. Okay. So now, what will the electric field look like if you have this kind of a sphere, right? If R is the radius, inside it will be zero. Outside from onwards, you are enclosing charge. The enclosed charge is what? Q by 4 pi r square epsilon naught. Okay. So because the sphere is bigger and bigger, okay. So if you drew a bigger sphere, right, the corresponding surface area is what? 4 pi. If you say K, it will become 4 pi K square. The charge enclosed is fixed. There's only Q in the inside. Outside, the further you go, the lower the electric field, which is natural, right? If you go very far, you will have less electric field because the flux that is being covered is constant. Like if you thought of flux like a fluid, the flux that is being covered is a constant because it's Q by epsilon, which is only determined by the enclosed charge. But the further you go, the field is lesser because the area is greater. The area 4 pi r square is becoming bigger and bigger and bigger as you go further and further away. Okay, so that is one way to understand Gauss's law in this context. Okay, so see, we have few more minutes, just a few more minutes. So I'm going to take a break because this Gauss's law is a little bit difficult. So I'm going to now stop presenting, and if you have any questions, you can ask. This is a good time to ask. Okay. My aim is to do a couple of problems, but see, I want to do it next time. Okay. If you have a question, you can ask. Otherwise, what if you let me see? Is there a question? No questions. Okay. So if you don't have questions, what I suggest is that you try to do some. You read the material. If you can see, you can use our app. If you use our app, it will come with the videos. So then you look at the chapter on Gauss's law and you see it with the videos. Otherwise, you can just download the textbook from your then you try to understand this chapter on Gauss's law. Okay. And if you have questions, you can start ask me in the beginning of the class. Otherwise, what I suggest is if you have our app, then what you try to do is read the text little bit. Look at these slides will come with the text, with the app, so you can see the slides. You can also listen to the IIT PAL lectures. Then you understand the material and build your understanding around Gauss's law. Okay, so see, we have done 1, 2, 3 parts of electrostatics. Then this is first time when you touch electrostatics, it doesn't feel so easy, but as you build confidence, you do more problems. Next time I will do some problems with Gauss's law. We have done little problems with electric field. We have not done maybe enough with electrostatic potential. So next class I will start with 1 or 2 questions, but before that I suggest that you also try some questions little bit. First time everything will be difficult. Everything will be difficult. First day, anything you learn is difficult. Okay, so but if you start early, then next day it will become easier. Then so we can then discuss next time. I'll do some questions. You can then solve some questions. Then you can do more, and then you can build confidence. Slowly, one builds confidence. You don't, as they say, Rome wasn't built in a day, right? If you see everything, is built over a long period of time, right? But these things you can learn quickly. Okay, so first try some, read the material, try some problems, and then we can continue discussing next class. All right. So I will see you all again next Saturday for mechanics, Sunday for electrostatics. Next time I'll try to do more with Gauss's law. Still few more slides, but I didn't want to finish everything this time. We'll do some problems, then we'll complete the Gauss's law, and then you would have done almost all of electrostatics, and then we will go to current, and we'll start with current electricity. Then actually we still have to do capacitance, but let me do a little bit of justice to capacitance. Once we do capacitance, then we'll go to current electricity, then we will go to electromagnetism. So that is the typical order in which electricity and magnetism is taught. So we'll do 1, 2, and 3, and then we will cover all some other extra material is there. So read the material, become familiar, do some problems, and I will see you next class. Okay, and also be ready for the other one, mechanics. Okay, and we will keep moving forward. See, I don't keep tests, but at some point we have to think in those terms also. Okay, I will give you something. It's not for me to evaluate you. It's for you to learn for yourself. Okay, so build your confidence in preparation for the time when we will move towards. You still have at least 1 year. Some of you have 2 years, right? So, but get ready. Keep doing stuff. Learn the material well. All right. I'll see you next week.